Hello, in this lecture we'll answer on two questions. In the first question, we find out the radius of this small circle. In the second question, we find out the area of this green shape. We start with the first question. So in the drawing, we have a quarter circle. AOB is a quarter circle. We know actually that the radius of this quarter circle OB equals to 16 units in its length. Side OB equals to 16 units. Inside this quarter circle AOB we have this semicircle and this small circle. And our mission is to find out the radius of this small circle or the value of R. Okay. So first of all, we know that AOB is a quarter circle, therefore this angle AOB equals to 90 degrees in its side. So the right angle in addition, side AO must be equal to side OB. They are both the radii of this quarter circle, therefore they are equal to each other. But the radius OB equals to 16, therefore the radius AO must be also equal to 16 units in its length. So I write it down. AO equals to 16, it is also the radius of this quarter circle. In the next step, we will define the relevant points to this question with letters. We will define the center of this quarter circle, this point, as point P. We will define the center of this small circle, this point, as point Q. We will define the point of tendency of tangent OB with this circle, this point, as point M. We will define the touching point of this semicircle with this small circle, this point, as point S. And finally, we define the point of tendency or the touching point of this big quarter circle with this small circle, this point, as point T. AO is the radius of this quarter circle and it is equal to 16 units in its length. But AO is also the diameter of this semicircle. So we know that the diameter of this semicircle equals to 16, therefore the radius must be equal to half of it. That is to say, it must be equal to 16 over 2, that is 8. So the radius AP of this quarter circle must be equal to 8 units in its length. And the radius PO must be also equal to 8 units in its length. Here we can implement rule 1. Why? Because we have the radius QM of this small circle, the radius QM that is equal to R is drawn to point M, that is the point of tendency of tangent OB with the small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OB will be perpendicular to the radius MQ. If OB is perpendicular to MQ, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1, which states that the tangent to a circle is perpendicular to the radius drawn to its point of tendency. In the next step, we will do a construction, that is to say, from point Q, that is the center of this small circle, we will draw perpendicular on AO. Again, from point Q, we will draw perpendicular on AO. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point Q and AO, this point as point H. By doing this construction, we created a quadrilateral HQMO. This is quadrilateral HQMO. Inside this quadrilateral, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore this fourth missing angle must be equal to 90 degrees in each side. So inside quadrilateral HQMO we have 4 right angles. And we know that according to rule 6, any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to this quadrilateral QMO as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle HQMO, side QA must be equal to the opposite side HO, but QM is R, therefore HO must be also equal to R. What is the length of this line segment PH? From the drawing it is very easy to see that PH equals to PO minus HO. Again, PH equals to PO minus HO. So I write it down. PH equals to PO minus HO. So PH equals to PO. PO is 8. It is the radius of the semicircle. That is equal to 8. Minus H cube. We just write down minus HO. HO equals to R according to what we already found out. So in total we actually found out that PH equals to 8 minus R units in its length. This side, I said PH equals to 8 minus R units in its length. Okay, so here in the drawing we have an external line between this semicircle and this small circle. That is to say, those two circles they are touching each other externally at point S. And whenever you have an external notch between two circles, you can implement rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes through their touching points. So in the drawing we have two circles. Those two circles touch each other externally at point P. Point P is their touching point. The center of this circle is here at point O. The center of this circle is here at point M. And the straight line that connects their centers together is of course the straight line OM. This straight line OM, according to rule 10, must pass from point to their touching point, that is point P. Or OPM is one straight line. OPM is one straight line according to rule 10. We can actually implement rule 10 in our drawing. Why? Because in our drawing the semicircle touches the small circle at point S. So they have an external notch between them at point S. The center of this semicircle is at point P. The center of this small circle is here at point Q. And the straight line that connects their centers together is the straight line PQ. And this straight line PQ must pass through their touching point, that is point S. Or PSQ is one straight line. Again, PSQ is one straight line. So I connect points P and Q together by straight line, and the straight line PQ must pass through their touching point, that is S. So I can see that the straight line PQ passes from the touching point, that is point S. So PSQ is one straight line. But what is exactly the definition of line segment PS? Line segment PS starts from point P, that is the center of the semicircle, and ends at point S, that is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore, PS is the radius of this semicircle, that is equal to 8 units in its length. Likewise, what is the definition of line segment QS? Line segment QS starts from point Q, that is the center of this small circle, and ends at point S, that is the point of the small circle itself. So this is exactly the definition of a radius. Therefore, QS is the radius of this small circle, that is equal to R. And because of the fact that according to rule 10, PSQ is one straight line, PSQ is one straight line, it means that PQ in total will be equal to PS plus SQ. Again, PQ must be equal to PS plus SQ because of the fact that PSQ is one straight line. So I write it down. PQ equals to PS plus SQ. So PQ equals to PS, that is 8, it is the radius of the semicircle, plus SQ. SQ is R, it is the radius of the small circle. So in total, PQ equals to 8 plus R. PQ equals to 8 plus R. In the next step, I'll copy the right green triangle PHQ in a new page, and we will implement the Pythagoras theorem on this right green triangle PHQ. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Side period equals to 8 minus R. And the hypotenuse PQ equals to 8 plus R. Here, PQ equals to 8 plus R. Side HQ is the missing side. Here by PT is the relation for Pythagoras theorem. So hopefully this is the right green triangle PHQ that I got from the original drawing. In this right triangle PHQ, according to the Pythagoras theorem, PQ square equals to PH square plus HQ square. And PQ square equals to PH square plus HQ square. So write it down. PQ squared, that is the square of the hypotenuse, equals to PH squared plus HQ squared. PQ, the hypotenuse PQ is 8 plus R, therefore PQ squared is 8 plus R squared. And it is equals to PH squared. PH is 8 minus R, therefore PH squared is 8 minus R squared. Plus HQ squared. HQ is the missing side, so we leave it as it is. So we found out that according to the Pythagoras theorem, we found out that 8 plus R squared equals to 8 minus R squared plus HQ squared. We will open the brackets on both sides of this equation and we get that 8 plus R squared equals to 8 squared, it is 64, plus R squared, plus 2 times 8 is 16, times R, so it is 16R, equals to 8 minus R squared. 8 minus R squared equals to 8 squared, it is 64, plus r square minus 2 times 8, this is minus 16 times r, so it is minus 16r plus hq square. So here we have 64 on both sides of this equation. So 64 will get cancelled, and we have r square also on both sides of this equation, so r square also will get cancelled. After we cancel those two expressions, in this side of the equation we left only with 16r. On the other side of the equation we have minus 16r plus hq square. Plus hq square. So 16r equals to minus 16r plus hq square. Here we add 16r to this equation and we get that 16r plus 16r is 32r. So 32r equals to hq square. 32r equals to hq square. Here we substitute 32 by 16 times 2. So 32 is 16 times 2 times r equals to hq square. Here we take a root out of this equation and finally get that hq, that is inside hq, is equals to the square root of 16 is 4, and inside the root we left only with 2r. So if we found out that the limit inside hq equals to 4 times square root of 2r units in its length. This is the limit inside hq, and it is equals to 4 times square root of 2 times r. But we already found out that quadrilateral HQMO is a rectangle, and we also know that the opposite sides of a rectangle are equal to each other. So in a rectangle HQMO, side HQ must be equal to the opposite side MO. But HQ is 4 times square root of 2r, therefore MO must be also equals to 4 times square root of 2r. So I write it down. MO equals to 4 times square root of 2r. So in the drawing, the small circle touches the big quarter circle here at point T. Point T is the touching point. So we have here an internal notch between the small circle and the big quarter circle. And whenever you have an internal notch between two circles, you can implement rule 9. I'll repeat quickly on rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together passes for their touching points. So in the drawing we have two circles, and the center of this big circle is here at point O. The center of this small circle is here at point M. And the straight line that connects the centers together is of course the straight line OM. So according to this rule 9, the straight line OM must pass through point P, that is their touching point. Again, the straight line OM must pass through point P, that is their touching point. Or OMP is one straight line. Again, OMP is one straight line. Okay? So I can actually implement rule 9 in our drawing. We have here an internal notch between the small circle and the big quarter circle. So according to rule 9, first of all we know that the center of the big quarter circle is here at point O. The center of this small circle is here at point Q. And the straight line that connects their centers together is of course the straight line OQ, and according to rule 9, the straight line OQ must pass for their touching point, that is point T. Or OQT is one straight line. Again, according to rule 9, OQT is one straight line. So I connect points O and T together by a straight line, and according to rule 9, the straight line OT must pass for point Q. Okay. can see the straight line OQ that connects the sensors together passes through point T, that is their touching point. OQT is one straight line. Therefore, if OQT is one straight line, it means that OT is a straight line. But what is the definition of the straight line OT? The straight line OT starts from point O, that is the center of the quarter circle, and then at point T, that is the point of the quarter circle itself. This is exactly the definition of a radius. Therefore, OT is the radius of this quarter circle, that is equal to 16 units in its length. According to what is given as the question, the radius of the quarter circle is 16. So, the radius OT equals to 16, it is the radius of the quarter circle. And what is the definition of line segment QT? Line segment QT starts from point Q, that is the center of the small circle, and then at point T, that is the point of the small circle itself. So this is exactly the definition of a radius. Therefore, QT is the radius of this small circle, that is equal to R. R is the radius that we are looking for in this question. And because of the fact that according to rule 9, OQT is one straight line, it means that OQ must be equal to OT minus QT. Again, OQ must be equal to OT minus QT. Repeat again. OQ must be equal to OT minus QT. So OQ equals to OT, that is 16, this is the radius of the quarter circle, minus QT. QT equals to R. So in total, OQ equals to 16 minus R. OQ equals to 16 minus R units in its length. So I write it down here. OQ equals to 16 minus R. In the next step, I'll copy the right blue triangle OQM in a new page, and we'll implement the Pythagoras theorem on this right blue triangle OQM. Here by PT is the abbreviation for Pythagoras theorem. Side QM equals to R, it is the radius of the small circle, that is the radius that we are looking for in this question. We have already found out that OM equals to 4 times square root of 2R. And the hypotenuse OQ equals to 16 minus R. So actually, this is the right blue triangle OQM that I copied from the original domain. In this right triangle OQM, according to the Pythagoras theorem, QO square equals to QM square plus MO square. Again, QO square equals to QM square plus MO square. So I write it down. QO square, that is the square of the hypotenuse, equals to QM square plus OM square. QO, the hypotenuse QO equals to 16 minus R, therefore QO square equals to 16 minus R square. And it must be equal to QM square. QM is R, therefore QM square is R square plus OM square. OM is 4 times square root of 2r, therefore OM squared is 4 times square root of 2r squared. Here we open the brackets on both sides of this equation, and we get that 16 minus r squared equals to 16 squared, that is 256, plus r squared, minus 2 times 16 is minus 32 times r, so it is minus 32r, and it is equal to r squared, plus 4 times square root of 2r squared equals to 4 squared, that is 16. And here we have square root of 2r squared is 2r, because the power cancels the root, and we're left only with 2r. So 256 plus r squared minus 32r equals to r squared, and 16 times 2r is 32r. So here we have r squared on both sides of this equation, so r squared will get cancelled. After cancelled r squared, in this side of the equation we have only with 256 minus 32r equals, on the other side of the equation we left only with 32r. So 256 minus 32r equals to 32r. Here we add 32r to this equation, and we get that 256 equals to 32r plus 32r is 64r. 256 equals to 64r. Here we divide this equation by 64, and we get that r equals to 256 over 64 is 4. So r equals to 4 units in its length. So we found out that the radius of this small circle r is equals to 4 units in its length. So we finished with the first question. In the next step, I will present to you the second question, and we'll solve the second question in two different methods. So in the drawing, we have a quarter circle, A or B is a quarter circle, side OB equals to 2 units in its length. This is angle DCB, that is the right angle, it is equal to 90 degrees in its size. And our mission is to find out the area of this green shape. This green shape, it is actually the right triangle DCB. So actually, in other words, our mission is to find out the area of the green right triangle DCB. So first of all, we know that AOB is a quarter circle, therefore this angle AOB equals to 90 degrees in its size. In addition, we know that side AD equals to side DO, or line segment AD equals to line segment DO. And we also, because of the fact that AOB is a quarter circle, sides AO and OB, they are above the diameter, they are above the radii of this quarter circle, therefore they are equal to each other. But the radius OB equals to 2, therefore the radius AO must be also equal to 2 units in its length. Okay. We know that AD equals to DO, according to what is given as a question. So if we define the length of line segment AD, this line segment AD is x, then DO must be also equal to x because they are equal to each other. AD is x, DO is x. So AD, that is x, plus DO, that is also x, is x plus x. And AD plus DO equals to AO. So in total, x plus x equals to AO. X plus x equals to AO. But AO equals to 2, therefore x plus x equals to 2. X plus x is 2x. 2x equals to 2. We divide this equation by 2, and finally we get that x equals to 1 unit in its length. So line segment AD is equal to X is equals to 1 unit in its length. And line segment DO that is also equals to X is equals to 1 unit in its length. In the next step, I'll copy the right white triangle DOB in a new page and we'll implement the Pythagoras theorem in this right white triangle DOB. Side DO equals to 1 unit in its length, and side OB of the right triangle DOB equals to 2 units in its length. Here by PT is a version for Pythagoras theorem. So actually, this is the right triangle DOB that I go from the original domain. We only do the Pythagoras theorem in this right triangle DOB. dB square equals to DO square plus dB square. So I write it down. dB square, this is the square of the hypotenuse, equals to DO square plus this, actually this DOB. This is dB square equals to DO square plus OB square. dB, the hypotenuse dB is the missing side, so we leave it as it is. So dB square equals to DO square. DO equals to 1, therefore DO square is 1 square, that is 1, plus dB square. dB is 2, therefore dB square is 2 square, that is 4. So in total dB square equals to 1 plus 4, that is 5. dB square equals to 5. The square of the hypotenuse equals to 5. We take a root out of this equation and we get that dB equals to the square root of 5 units in its length. So dB equals to the square root of 5 units in its length. In the next step, we will do a construction, that is to say, we complete this quarter circle to a circle. So completed this quarter circle to a circle. In the next step, we'll extend the radius BO by straight line until it touches the circle here at this point. And we'll define the touching point of the extended radius BO with this circle at this point as point P. So BO as a radius, it is absolutely a straight line. We extended the straight line BO by straight line, therefore the result must be a straight line. Extended straight line by straight line, the result must be a straight line. So the result BP is a straight line. So we know that BP is a straight line. So if you focus on the upper side of this straight line BP at point O, here the sum of the angles must be equal to 180 degrees, according to rule 3 that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of PB at point O. We have this angle that is the right angle plus the missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. What is the definition of line segment PO? Line segment PO starts from point O, that is the center of the circle, and that's at point P, that is the point on the circle itself. So this is exactly the definition of a radius. Therefore, OP is the radius of this circle that is equal to 2. We just right now found out that BP is a straight line. BP is a straight line, but BP is a straight line that touches the circle at 2 points, B and P. And any straight line that touches the circle at 2 points is defined as a chord. So BP is a chord. BP is a chord that passes through point O, that is the center of the circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, BP is the diameter of the circle. So write it down. BP is the diameter of the circle. In the next step, we'll extend side CD by straight line until it touches the circle. Repeat again. We'll extend this side CD by straight line until it touches the circle. But the question is where the extended side CD will touch the circle. We will assume that the extended side CD will not touch a circle at point P, but in any other point. For example, we will assume that the extended side CD will touch the circle at this point. We'll define the touching point as point G. Actually, by doing this construction, we get the peripheral angle BCG. This is peripheral angle BCG. And peripheral angle BCG equals to 90 degrees in its size, because we know that this angle equals to 90 degrees. So peripheral angle BCG equals to 90 degrees in its size. And this peripheral angle BCG is subtended on BG. Peripheral angle BCG is subtended on BG. And BG is definitely not the diameter of the circle, because we already found out that from point B we have the diameter BP. And from point B we can have only one diameter. And the only diameter that we found from point B is BP. Therefore, BG is definitely not the diameter of the circle. And that is a contradiction to rule 5, because we have peripheral angle BCG is equal to 90 degrees in its size, and still it doesn't subtend on the diameter of the circle. But because it's subtended on BG, that is not the diameter of the circle. Okay. I repeat again on rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees in size must be subtended on the diameter of the circle. We have a peripheral angle MAN, and this peripheral angle MAN equals to 90 degrees in its size, and indeed it's subtended on MN, that is the diameter of the circle. It is the diameter of the circle. And here, actually, have peripheral angle BCG. This is equal to 90 degrees in its size. It doesn't subtend on the diameter of the circle, because it's subtended on BG, that is not the diameter of the circle. It is a contradiction to rule 5. Therefore, our assumption that the extended side CD will touch the circle at point G is incorrect. Therefore, we must conclude that the extended side CD will touch the circle at point P. At point P and not in any other point. In this way, we'll avoid contradiction to rule 5. Why? Because now we have peripheral angle BCP that's equal to 90 degrees in its size, and this peripheral angle BCP that's equal to 90 degrees in its size is subtended on PB, that is the diameter of the circle, exactly according to rule 5. Okay. In the next step, I'll copy the right triangle PDO in a new page and implement the Pythagoras theorem on this right triangle PDO. So this is the right triangle PDO that the copied from the original drawing. According to the Pythagoras theorem, this right triangle PDO, PD squared, that is the square of the hypotenuse, must be equal to PD square must be equal to EO square plus PO square. PD is the missing side, so we leave it as it is. So PD square equals to DO square. DO is 1, therefore DO square is 1 squared, that is 1. Plus PO square. PO equals to 2, therefore PO square is 2 squared, that is 4. So in total PD square equals to 1 plus 4, that is 5. PD square equals to 5. We take a root out of this equation and finally get that PD equals to the square root of 5 units in its length. PD equals to the square root of 5 units in its length. This side PD is equal to the square root of 5 units in its length. In the next step, we'll extend the radius AO by a straight line until it touches the circle. And we'll define the touching point of the extended radius AO with this circle. This point is point Q. What is the definition of line segment OQ? Line segment OQ starts from point O, that is the center of the circle, and that's at point Q, that is the point of the circle itself. So this is exactly the definition of a radius. Therefore, OQ is the radius of this circle, that is equal to 2 units in its length. So here we can implement rule 11. I'll repeat quickly on rule 11. According to rule 11 is true in any circle. So in any circle, if chord AB intersects with chord CD at point O, again chord AB intersects with chord CD at point O. Then in this point, the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can actually implement rule 11 in our drawing. Why? Because in our drawing we have chord AQ. This is chord AQ intersects with chord CP. This is chord CP at point D. Again, chord AQ intersects with chord CP at point D. So I write it down. Chord AQ intersects with chord CP at point D. it again. Now original drawing, chord AQ intersects with chord CP at point D. Therefore, according to rule 11, the following equation will be true. That AD times DQ, AD times DQ equals to CD times DP. Again, AD times DQ equals to CD times DP. So write it down. AD times DQ equals to CD times DP. Repeat again, according to rule 11, we get that the following equation is true, that AD times DQ equals to CD times DP. Okay. AD is 1 times DQ. DQ in total equals to 1 plus 2, that is 3. Again, DQ in total equals to 1 plus 2, that is 3. And it is equals to CD. CD is the missing side, so we leave it as it is. Times DP. We already found out that DP equals to the square root of 5 units. So according to rule 11, we found out that 1 times 3 equals to CD times square root of 5. So 1 times 3 is 3, so 3 equals to the square root of 5 times CD. 3 equals to square root of 5 times CD. Here we divide this equation by square root of 5. And we get that CD, the missing side CD, is equals to 3 over square root of 5 units in its length. So actually, this is the missing side CD, and it is equal to 3 over square root of 5 units in its length. So I write it down. In the next step, I'll copy the right ring triangle DCB in a new page, and we'll implement the Pythagoras theorem on this right ring triangle DCB in order to find out the missing side CB. I will remind you that our mission is to find out the area of this green right triangle DCB. Here by PT is a relation for Pythagoras theorem. So friends, this is the right green triangle CDB that I got from the original drawing. Here we already found out that side DC equals to 3 over square root of 5 units in its length. And the hypotenuse DB equals to the square root of 5 units. So according to the Pythagoras theorem, this right triangle DCB, DB squared, that is the square of the hypotenuse, must be equal to DC squared plus CB squared. the hypotenuse dB equals to the square root of 5, therefore dB squared square root of 5 squared, that is 5, and it is equals to dc squared. dc is 3 over square root of 5, therefore dc squared is 3 over square root of 5 squared, plus cb squared. cb is the missing side, so we leave it as it is. So 5 equals to 3 over square root of 5 squared. 3 over square root of 5 squared equals to 3 squared, that is 9, over square root of 5 squared, that is 5. So in total, this expression 3 over square root of 5 squared equals to 9/5 plus cb squared. cb is the missing side, so we leave it as it is. So we found out that 5 equals to 9/5 plus cb squared. We will subtract 9/5 from this equation, and we get that 5 minus 9/5 equals to cb squared. So here we'll multiply 5 by 5 and then we divide it by 5 in order to overcome a factor with 9 over 5. 5 times 5 is 25, so in total in the numerator of this expression we have 25 minus 9 divided by 5, and it is equals to cb squared. 25 minus 5 is 16, so in total this expression equals to 16 over 5. That is equals to cb squared. Here we take a root out of this equation, and finally we get that the missing side cb is equals to the square root of 16, that is 4 over square root of 5. But again, the missing side cb equals to 4 over square root of 5 units. So I write it down in the original drawing. This side cb equals to 4 over square root of 5 units in its length. Our mission is to find out the area of this green shape. This green shape is actually the right green triangle DCB. So the area of the green shape is actually equal to the area of this green right triangle DCB. The area of green triangle equals to the base of the triangle times the height to the base over 2. Repeat again, the area of any triangle equals to the base times the height to the base over 2. We'll choose the base of this green right triangle DCB as DC. Therefore the height must be CB. Why? Because CB creates 90 degrees with the base CD. This angle equals 90 degrees. So repeat again. You choose the base of the green right triangle DCB as DC, and the height is CB over 2. The base DC is 3 over square root of 5 times the height CB is 4 over square root of 5 divided by 2. So for we found out that the area of the green shape equals to the value of this expression, and this expression equals to 3 times 4 is 12 over square root of 5 times square root of 5 is 5 over 2. 12 over 5 over 2 equals to 12 over 5 times 2. So it is equals to 12 over 5 times 2. 5 times 2 is 10. We divide both the numerator and the denominator of this number by 2. 12 over 2 is 6. Over 10 over 2 is 5. So in conclusion, we found out that the area of this green shape equals to either 6/5 square units, or in terms of numbers, it is equals to 1.2 square units. So we finished with the first method. the next step I will present to you how to find out the area of this grain shape according to the second method. So A or B is a quarter circle, therefore this angle A or B equals to 90 degrees. The radius OB equals to 2. The radius AO also equals to 2. We have already found out that AD equals to 1. We know that AD equals to DO. We already found out in the first method that AD equals to 1 and DO also equals to 1. Actually, implement that. Now we will complete this quarter circle to a circle. Now completed the quarter circle to a circle. We'll extend the radius BO by a straight line until it touches the circle. We define the touching point of the extended radius BO with this circle. This point is P. I already explained to you that in the first method that BP is a straight line. So if you focus on the upper side of the straight line BP at point O, the sum of the angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be also equal to 90 degrees in its size. Again, I already explained to you in the first method that BP is a straight line that touches the circle at 2 points B and P, and it passes through the center of this circle. Therefore, BP is a chord that passes through the center of the circle, and any chord that passes through the center of the circle must be the diameter of the circle. Therefore, BP is the diameter of the circle. BP is the diameter of the circle. And then we did the construction in the first method. That is to say, we extended side CD until it touches the circle. And I already proved to you that when you extend side CD, it must touch the circle at point P and not in any other point. Otherwise, you have contradiction to rule 5. OP is the radius of the circle, that's equal to 2 units. Here we have the right triangle PDO. According to the Pythagoras theorem, in this right triangle PDO, 2 square plus 1 square equals to PDO square. 2 square is 4 plus 1 square is 1. 4 plus 1 is 5, and the square root of 5 is actually PD, the opposite PD equals to the square root of 5. Okay. Actually, we did all the steps that I do that I'm doing here in the first method, so I'll not repeat on them. So in the next step, we'll focus on the right triangle PDO, and we'll define this angle DPO as theta. So in the right triangle PDO, this angle equals to theta, this angle equals to 90 degrees, therefore the missing third angle, this missing third angle must be equal to 90 degrees minus theta. Y equals 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Therefore, this third missing angle must be equal to 90 degrees in its size. 90 degrees minus theta in its size. Again, 90 degrees minus theta plus theta is 90 degrees. 90 degrees minus theta plus 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Therefore, the missing angle here must be equal to 90 degrees minus theta. Likewise, if we focus on the big right triangle PCB, the big right triangle PCB, this angle equals to theta, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus theta. In the next step, we'll prove that the big right triangle PCB is similar to this small right triangle PDO. So I write it down. We prove that the big right triangle PCB is similar to this small right triangle PDO. So why the big right triangle PCB is similar to the small right triangle PDO? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So this is angle PCB, in the right big triangle PCB, and it is equal to this angle, this is actually angle POD, in the right small triangle PDO. I'll repeat again. Angle PCB in the right big triangle PCB equals to angle PDO in the small right triangle PDO. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta. This is a common angle, it belongs to both triangles. Therefore we can write down that angle theta equals to itself. It's a common angle that belongs to both triangles. So if we relate to this angle theta as it belongs to the big right triangle PCB, it will be defined as angle CPB. And it equals to itself. So if we relate to angle theta as it belongs to the small triangle DPO, it will be defined as angle DPO. Repeat again. This equation means that angle theta equals to itself. We just call to angle theta two different names. Angle theta equals to itself is a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So roughly, this is angle PBC. In the big right triangle PCB, and it is equal to this angle the section angle PDO in the small right triangle PDO. Repeat again, after I found out that angle PBC in the big right triangle PCB equals to angle PDO in the small right triangle PDO. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually found out that all the triangles in the right big triangle PCB are correspondingly equal to all the triangles in the right small triangle PDO. Therefore, the big right triangle PCB is similar to the small right triangle PDO according to angle similarity rule. So I write it down. The big right triangle PCB is similar, this is the sign of similar, to the small right triangle PDO according to angle similarity rule. And from the fact that the big right triangle PCB is similar to the small right triangle PDO, we derive that the following relationship exists between their sides. We will derive that side DP in the small triangle PDO over side PB in the big triangle is equal to side DO in the small triangle over side CB in the big triangle, and it is also equal to side PO in the small triangle over side PC in the big triangle. And again, I found out that dP over DO, dP over PB equals to DO over CB equals to PO over PC. dP is equal to 5 over PB. PB is the diameter of this circle, and it is equal to 2 plus 2, that is 4. So PB is 4, and it is equal to DO. DO is 1 over CB. CB is the missing side, so we leave it as it is. And it is equal to PO. PO is 2 over PC or CP. CP in total equals to CD plus square root of 5. Again, CP in total equals to CD plus square root of 5. So actually, according to equation 1, I found out that square root of 5 over 4 equals to 1 over CB equals to 2 over CD plus square root of 5. Those two expressions are equal to each other, so we get equation 1 from those two expressions that are equal to each other. So according to equation 1, square root of 5 over 4 equals to 1 over CB. Here we cross multiply this equation 1, and we get that according to this equation 1, square root of 5 times CB equals to 4. So here we divide this equation 1 by square root of 5. And finally get that according to this equation 1, CB equals to 4 over square root of 5 units in its length. This is side CB, and it is equals to 4 over square root of 5 units. Here we have those two expressions, they are equal to each other, therefore we get the equation 2 from those two expressions that are equal to each other. So according to equation 2, we get that square root of 5 over 4 equals to 2 over CD plus square root of 5. Repeat again. According to equation 2, we actually found out that square root of 5 over 4 equals to 2 over CD plus square root of 5. Here we cross multiply this equation 2. And we get that according to equation 2, square root of 5 times CD plus square root of 5 equals to 2 times 4 is 8. Here we open the brackets on this side of this equation 2, and we get that square root of 5 times CD and square root of 5 plus square root of 5 is 5 equals to 8. So here we subtract 5 from this equation 2, and we get that square root of 5 times CD equals to 8 minus 5 is 3. So square root of 5 times CD equals to 3. Here we divide this equation 2 by square root of 5. And finally we get that according to this equation 2, CD, the missing side CD equals to 3 over square root of 5 units. So the missing side here, CD equals to 3 over square root of 5 units in its length. Our mission is to find out the area of this green shape. It's actually the area of the green right triangle CDB. And we know that the area of any triangle equals to the base of the triangle times the height to the base over 2. Again, we choose the base as CD, and the height is CB because it creates 90 degrees with the base. So the height is CB divided by 2. And again, the base of the green triangle is CD, the height is CB over 2. CD equals to 3 over square root of 5. Times CB. CB equals to 4 over square root of 5 divided by 2. So we actually found out that the area of the green shape equals to the value of this expression. and the value of this expression equals to 3 times 4 is 12, over square root of 5 times square root of 5 is 5 over 2. 12 over 5 over 2 equals to 12 over 5 times 2. So it is 12 and 5 times 2 is 10. So it is 12 times 10. We divide both the numerator and the denominator of this number by 2. 12 over 2 is 6 and 10 over 2 is 5. So in conclusion, option found out that the area of this green shape equals to either 6/5 square units, equals to either 6/5 square units, or in terms of numbers, it is equals to 1.2 square units. Right, so we finish with the second method. In the next step, I'll summarize the lecture. We'll start with the first question, of course. In the first question, our mission is to find out the radius of this small circle. So, in the drawing, we have a quarter circle, AOB. AOB is a quarter circle. The radius of this quarter circle, OB, is 16. Inside this quarter circle, we have this semicircle and this small circle. Our mission is to find out the radius of this small circle, or the value of R. Okay, so first of all, we know that AOB is a quarter circle, therefore this angle AOB equals to 90 degrees in its size. In addition, sides AO and OB, they are both the radii of this quarter circle, therefore they are equal to each other. But it is given us the question that the radius OB of the quarter circle equals to 16, therefore the radius AO must be also equal to 16. And here, the radius AO of the quarter circle is also the diameter of this semicircle. So the diameter of this semicircle AO is 16, and therefore the radius must be equal to half of it. That is to say, the radius must be equal to 16 over 2, that is 8. So the radius AP of this semicircle equals to 8, and the radius PO is also equals to 8. Okay, here we implemented. So we know that PO equals to 8. So here we implemented the whole one. In this drawing, we have the radius QM, that is drawn to point M, that is the point of tendency of tangent OB with this small circle. And whenever we have a radius that is drawn to the point of tendency, then tangent OB will be perpendicular to the radius MO. If OB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we did a construction, that is to say, from point Q, we drew perpendicular on AO. Again, from point Q, that is the center of this small circle, we drew perpendicular on AO. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and AO. This point is point edge. By doing this construction, we added quadrilateral Q edge OM. Inside this quadrilateral Q edge OM, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule. Then the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral HQMO we have 4 right angles, and according to rule 6, any quadrilateral that has 4 right angles must be this rectangle plus a square. So we relate to this quadrilateral HQMO as a rectangle because it has 4 right angles. But we also note that the opposite sides of a rectangle are equal to each other. So in rectangle HQMO, side QM must be equal to the opposite side HO, but QM equals to R, therefore HO must be also equal to R. R is the radius of this small circle, the radius that we are looking for in this question. So HO equals to R, PO equals to 8, it is the radius of the semicircle. So in total, PH must be equal to PO minus HO. Here, PH must be equal to PO minus HO. So PH equals to PO, that is 8, minus HO, that is R. So in total, PH equals to 8 minus R. So here we have an external match of this semicircle with this small circle. That is to say, they are touching each other externally at point S. And here we can implement rule 10. I'll repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes through their touching point. So here we have those two circles. They are touching each other externally at point P, this point. The center of this circle is at point O. The center of this circle is at point M. And the straight line that connects their centers together is of course the straight line OM. And this straight line OM, according to this rule 10, must pass through their touching point, that is point P. Or OPM is one straight line. Again, OPM is one straight line according to this rule 10. We can actually implement rule 10 in our drawing, because in our drawing, the semicircle has an external match with this small circle. They are touching each other externally at point S. The center of this semicircle is at point P. The center of this small circle is at point Q. And the straight line that connects the centers together is the straight line PQ. This straight line PQ must pass through point S, that is their touching point. Or PSQ is one straight line. Again, PSQ is one straight line according to rule 10. But what is exactly the definition of line segment PS? Line segment PS starts from point P, that is the center of the semicircle, and that's at point S, that is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore, PS is the radius of this semicircle, that is equal to 8 units in its length. Likewise, what is the definition of line segment QS? Line segment QS starts from point Q, that is the center of this small circle, and that's at point S, that is the point of the small circle itself. So this is exactly the definition of a radius. Therefore, QS is the radius of this small circle, that is equal to R. R is the radius that we are looking for in this question. So in total, PSQ is one straight line, therefore PQ is also a straight line. And therefore, because of the fact that PSQ is one straight line, it means that PQ will be equal to PS plus SQ. Again, PQ will be equal to PS plus SQ. Here, PQ equals to PS plus SQ. So PQ equals to PS, that is 8, it is the radius of the semicircle, plus SQ, that is R. R is the radius of the small circle. So in total, PQ equals to 8 plus R. We already found out that PH equals to 8 minus R. And HQ is the missing side in the right green triangle PHQ. So I orbit the right green triangle PHQ in a new page, and we implemented the Pythagoras theorem in this right triangle PHQ. This is the right triangle PHQ that according to the original domain, according to the Pythagoras theorem, in this right triangle PHQ, PQ square equals to PH square plus HQ square. PQ is 8 plus R, therefore PQ square is 8 plus R square. And it is equals to PH square. PH is 8 minus R, therefore PH square is 8 minus R square plus HQ square. HQ is the missing side, so we leave it as it is. We open the brackets on both sides of this equation and found out that 8 plus R square equals to 8 squared, that is 64, plus R square, plus 2 times 8, it is 16 times R. So it is plus 16R, and it is equals to 8 minus R square equals to 8 square, plus to 8 squared, it is 64, plus R square, minus 2 times 8, that is minus 16 times R. So it is minus 16R plus HQ square. So here we have 64 on both sides of this equation, so 64 will get cancelled. And we have R square also on both sides of this equation, so R square also will get cancelled. After cancelling those two expressions, in this side of the equation we left only with 16R. In the other side of this equation we left with minus 16R plus HQ square. So 16R equals to minus 16R plus H square, plus HQ square. Here we added 16R to this equation, and finally found out that 16R plus 16R is 32R. So 32R equals to HQ square. We substitute 32 by 16 times 2. So here 16 times 2 times r equals to hq squared. We took a root of this equation and finally found out that hq equals to the square root of 16, that is 4. Inside the root we left only with 2r. So in total I actually found out that hq equals to 4 times square root of 2r. So this is side hq that is equals to 4 times square root of 2r. We already found out that quadrilateral HQMO is rectangle, and we also know that the opposite sides of rectangle are equal to each other. So in rectangle HQMO, side HQ must be equal to side MO. But HQ is 4 times square root of 2r, therefore MO must be also equal to 4 times square root of 2r. So here the small semicircle touches the big quarter circle, the small circle. This is the small circle that touches the big quarter circle here at point T. So they have an internal match between them at point T. And therefore we can implement here rule 9. I'll repeat quickly on rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together passes through their touching point. So we have here two circles. The center of this big circle is at point O. The center of this small circle is at point M. And the straight line that connects their centers together is of course the straight line OM. And according to this rule 9, the straight line OM must pass through their touching point, that is point P. Or OMP is one straight line. Again, OMP is one straight line according to this rule 9. So we can actually implement all 9 in our drawing, because in our drawing, this small circle have an internal notch with the big quarter circle. That is to say, they are touching each other internally at point T. And therefore, according to rule 9, the center of the big quarter circle is here at point O. The center of this small circle is here at point Q. And the straight line that connects the centers together is the straight line OQ. According to rule 9, the straight line OQ must pass through point T, that is their touching point. OQT is one straight line. Again, OQT is one straight line according to rule 9. So I connected points O and Q, I joined points O and Q together by a straight line, and according to rule 9, the straight line OQ must pass through point T, or OQT is one straight line. If OQT is one straight line, it means that OT is also a straight line. But what is the definition of the straight line OT? The straight line OT starts from point O, that is the center of the quarter circle, and ends at point T, that is the point of the quarter circle itself. So this is exactly the definition of a radius. Therefore, OT is the radius of this quarter circle. It is equal to 16 units in its length. Here, OT equals to 16. And what is the definition of line segment QT? Line segment QT starts from point Q, that is the center of the small circle, and ends at point T, that is the point of the small circle itself. So this is exactly the definition of a radius. Therefore, QT is the radius of this small circle, that is equal to R. So in total, because of the fact that OQT is one straight line, according to rule 9, it means that OQ must be equal to OT minus TQ. Again, OQ must be equal to OT minus QT. So OQ equals to OT, that is 16, minus QT, that is R. So in total, OQ, this line segment OQ equals to 16 minus R. In the next step, I copied this right blue triangle OQM in a new page, and we implemented the Pythagoras theorem on this right triangle, triangle OQM. This is the right triangle OQM that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle OQM, OQ squared equals to QM squared plus MO squared. OQ is 16 minus R, therefore OQ squared is 16 minus R squared, and it is equals to OM squared. OM is 4 times square root of 2R, therefore OM squared is 4 times square root of 2R squared plus OM squared. OM is R, therefore OM squared is R squared. So in conclusion, we should have found out that 16 minus R squared equals to R squared plus 4 times square root of 2R squared. We open the brackets on both sides of this equation and finally found out that 16 minus R squared equals to 16 squared, that is 256, plus r squared minus 2 times 16, that is minus 32 times r, so it is minus 32r. On the other side of the equation we have r squared, and 4 times square root of 2r squared equals to 4 squared, that is 16, and square root of 2r squared equals to 2r. So in conclusion, we found out that 256 plus r squared equals to 32r. 256 plus r squared minus 32r equals to r squared, and 16 times 2r is 32r. So 256 plus r squared minus 32r equals to r squared plus 32r. Here we added 32r to this. We have r squared on both sides of the equation, so r squared will get cancelled. After we cancelled r squared, in this side of the equation we left only 256 minus 32r. In the other side of the equation we have 32r. So in total, we found out that 256 minus 32r equals to 32r. Here we added 32r to this equation, and found out actually that 256 equals to 32r plus 32r. 32r plus 32r is 64r. So 256 equals to 64r. We divided this equation by 64 and finally found out that r equals to 256 over 64 is 4. So we found out that the radius of this small circle r equals to 4 units. Okay, so we finished with the first question. In the next step, I actually presented to you the second question, and we solved the second question in 2 different methods. Our mission is in the second question is to find out the area of this green shape. The green shape is actually the right triangle DCB, so our mission is to find out the area of the right green triangle DCB. In the drawing we have a quarter circle, AOB is a quarter circle. We know that the radius OB of the quarter circle equals to 2. In addition, we know that AD equals to DO. And this angle DCB is a right angle. Again, our mission is to find out the area of this green shape. So first of all, we know that AOB is a quarter circle, therefore this angle equals to 90 degrees in its size. In addition, because of the fact that AOB is a quarter circle, it means that sides AO and OB they are both the radii of this quarter circle, therefore they are equal to each other. But the radius OB equals to 2, therefore the radius AO must be also equal to 2. Okay, so here AD equals to DO. So if we define AD as x, then DO must be also equal to x. AD, that is x plus DO, that is also x, equals to AO. But AO is 2, therefore AD plus DO equals to 2. So x plus x equals to 2. X plus x is 2x, so 2x equals to 2. We divided this equation by 2 and finally found out that x equals to 2 over 2, that is 1. So AD, that is x, equals to 1, and DO, that is also x, equals to 1. Then I copied the right triangle DOB in a new page and we implemented the Pythagoras theorem in this right triangle DOB. This is the right triangle DOB that I got from the original drawing. According to the Pythagoras theorem, this right triangle DOB, DB square equals to DO square plus OB square. DB is the missing side, so we leave it as it is. So DB square equals to DO square. DO is 1, therefore DO square is 1 square, that is 1. Plus DB square. DB is 2, therefore DB square is 2 square, that is 4. So in total, DB square equals to 1 plus 4, that is 5. DB square equals to 5. We took out all of this equation and finally found out that the hypotenuse DB equals to the square root of 5 units in its length. This is DB and it equals to the square root of 5 units in its length. In the next step, we did the construction, that is to say, we completed this quarter circle to a circle. And then we extended the radius BO by a straight line until it touches the circle at this point. We define the touching point of the extended radius BO of this circle, this point is point P. And here, OP is the radius of the circle, that is equal to 2. Then we extended side CD by a straight line until it touches the circle. Now, actually we don't know where the extended side CD will touch the circle. We'll assume that the extended side CD will touch the circle not at point P but in any other point, for example this point G. Okay, so by doing this construction we can get the peripheral angle BCG. This peripheral angle BCG equals to 90 degrees in its size, and still it doesn't is not subtended on PB, that is the diameter of the circle, but it is subtended on BG, it is not the diameter of the circle, because from point B we have only one diameter, that is BP. Therefore BG is definitely not the diameter of the circle, and we have contradiction to rule 5 because we have peripheral angle BCG that is the right angle and still is not subtended on the diameter of the circle. In order to avoid the contradiction to rule 5, we must conclude that the extended side CD will touch the circle at point P, and then we don't have any more contradiction to rule 5. Why? Because we have peripheral angle BCG that is equal to 90 degrees in its size and is subtended on PB, that is the diameter of the circle, exactly like rule 5. Okay, here we have the right triangle POD. In the right triangle POD, one side is 2, the other side is 1, therefore the hypotenuse must be equal to the square root of 5 units. Okay, and then actually extended the radius AO of this circle by straight line until it touches the circle. We define the touching point of the extended radius AO with this circle, this point as point Q. OQ is the radius of the circle, that is 2. So here we can implement rule 11. I'll repeat quickly on rule 11. According to rule 11, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can definitely implement rule 11 in our drawing. Why? Because in our drawing we have chord AQ that intersects with chord CP at point D. Again, chord AQ intersects with chord CP at point D. And whenever you have two chords that intersect with each other in a circle, you can implement rule 11. Repeat again. Now drawing, chord AQ intersects with chord CP at point D. Therefore, according to rule 11, the following equation will be true that AD times DQ equals to CD times DP. Again, AD times DQ equals to CD times DP. AD is 1, DQ is 3, CD is the missing side, DP is square root of 5. So actually found out that 3 equals to the square root of 5 times CD. We divided this equation by square root of 5 and finally found out that CD, the missing side CD, equals to 3 over square root of 5. This is the missing side CD, and it is equal to 3 over square root of 5 units in its length. In the next step, I copied the right green triangle CDB in your page and implemented the Pythagoras theorem of this right green triangle CDB in order to find out the missing side CB. So actually, this is the right green triangle CDB that I copied from the original drawing. The hypotenuse DB equals to the square root of 5 units. We just right now found out that CD equals to 3 over square root of 5 units. According to the Pythagoras theorem, this right triangle CDB, dB square equals to CD square plus CB square. Again, dB square equals to CD square plus CB square. dB is square root of 5, therefore dB square is square root of 5 square, that is 5, and it is equal to CD square. CD is 3 over square root of 5, therefore CD square is 3 over square root of 5 square plus CB square. CB is this missing side, so we leave it as it is. So 5 equals to 3 over square root of 5 equals to 3 squared, that is 9 over square root of 5 times square root of 5 is 5. So this expression in total equals to 9 fifths plus CB square. Here we subtracted 9 fifths from this equation and finally found out that CB square equals to 5 minus 9 fifths. Here we multiplied 5 by 5 and we divided by 5 in order to overcome a factor with 9 over 5. So 5 times 5 is 25. So in total, in the numerator of this expression, we have 25 minus 9 over 5. 25 minus 9 is 16. So this expression equals to, in total, to 16 over 5. 16 over 5 equals to CB squared. We took out of this equation and finally found out that CB, the missing side CB, equals to the square root of 16, that is 4, over square root of 5. So the missing side CB equals to 4 over square root of 5 units in its length. Our mission is to find out the area of this green shape. The area of the green shape equals to the area of the green right triangle DCB. And the area of the area of the triangle equals to the base of the triangle times the height to the base over 2. So the area of the green shape equals to the area of the right green triangle. The area of any triangle equals to the base of the triangle times the height to the base over 2. We choose the base of this green right triangle DCB as DC, and therefore the height is CB because it creates 90 degrees with the base DC. Again, we choose the base as CD, and the height is CB divided by 2. DC is 3 over square root of 5. CB is 4 over square root of 5 divided by 2. So the area of the green shape equals to the value of this expression. And the value of this expression is 3 times 4 is 12. Square root of 5 times square root of 5 is 5 divided by 2. 12 over 5 over 2 is 12 over 5 times 2. So it is 12 and 5 times 2 is 10. So in total, the area of the green shape equals to 12 over 10. We divided both the numerator and the denominator of this number by 2. 12 over 2 is 6. 10 over 2 is 5. So in conclusion, we found out that the area of this green shape equals to either 6/5 square units, or in terms of numbers, the area of this green shape equals to 1.2 square units. We finished with the first method. In the next step, I actually presented to you how to find out the area of this green shape according to the second method. So AOB is a quarter circle, therefore angle AOB equals to 90 degrees, and AO and OB they are both the area of the circle, therefore they are both equal to 2 units. We have already found out in the first method that AD equals to 1, D also equals to 1. So here we did a construction, that is to say, we completed this quarter circle to a circle. And then we extended the radius BO by straight line until it touches the circle. We define the touching point of the extended radius BO with this circle. This point is point P. When we extend the straight line by straight line, the result is a straight line. Therefore, BP is a straight line. If you focus on the upper side of the straight line BP at point O, here the sum of the angles must be equal to 180 degrees. So which angles we have here? We have this angle that is 90 degrees plus the missing angle. In total, they must be equal to 180 degrees. Therefore, this missing angle must be equal to 90 degrees in its size. So BP is a straight line, but BP is a straight line that touches the circle at 2 points, B and P. Therefore, BP is a chord. BP is a chord that passes through point O, that is the center of the circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, BP is the diameter of the circle. Okay, repeat again, BP is the diameter of the circle. We extended side CD until it touches the circle, and I already proved in the first method that when you extend side CD, it must touch the circle at point P, and only at point P and not in any other point. Okay, so we have here the right triangle DOP, this side equals to 1, this side equals to 2, therefore the hypotenuse must be equal to square root of 5 units instead according to the Pythagoras theorem. Then we focus on this right triangle DPO. In the right triangle DPO, we define this angle as theta. So in the right triangle DPO, this angle equals to theta, this angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right triangle PCB, this angle equals to theta, this angle equals to 90 degrees, therefore the missing third angle must be equal to 90 degrees minus theta. In the next step, we proved that the big triangle PCB is similar to the small white triangle PDO. So why the big triangle PCB is similar to the small white triangle PDO? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta. That is a common angle that belongs to both triangles, so we can write down that angle theta equals to itself is a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So we shall prove that all the three angles in the right triangle PCB are correspondingly equal to all the three angles in the right triangle PDO. Therefore, the big triangle PCB is similar to the small triangle PDO according to angle similarity rule. Repeat again. The big triangle PCB is similar to the small triangle PDO according to angle similarity rule. And from the fact that the big triangle PCB is similar to the white triangle PDO, we derive that the following relationship exists between their sides. We derive that side DP in the small triangle over side PB in the big triangle equals to side DO in the small triangle over side CB in the big triangle, and it is also equals to side PD in the small triangle over side PEC in the big triangle. DP is square root of 5, PB is 4, DO is 1, CB is the missing side, so we write as it is. Here, PO equals to 2, and PC equals to CD plus root of 5. Again, PC in total equals to square root of 5 plus CD. Square root of 5 plus CD. And again, here, PC equals to square root of 5 plus CD. So, we have here the wrong equation. Those two expressions are equal to each other, so we get equation 1 from those two expressions that are equal to each other. So according to equation 1, square root of 5 over 4 equals to 1 over CB. We can multiply this equation 1, and finally found out that square root of 5 times CB equals to 4. We divided this equation 1 by square root of 5, and finally found out that the missing side CB equals to 4 over square root of 5. This is the missing side CB, that is equals to 4 over square root of 5 units instead. We continue to focus on the long equation 1. In this equation 1, we have those two expressions that are equal to each other. Therefore, we created equation 2 from those two expressions that are equal to each other. So according to equation 2, we actually found out that square root of 5 over 4 equals to 2 over CD plus square root of 5. We cross multiply this equation 2, and finally found out that according to this equation 2, square root of 5 times CD plus square root of 5 equals to 4 times 2, that is 8. We open the brackets on this side of this equation 2, and finally found out that according to this equation 2, square root of 5 times CD, here we have square root of 5 plus square root of 5 is 5. So in total, this side of equation 2, we have square root of 5 times CD plus 5 equals to 8. Here we subtracted 5 from this equation 2, and finally found out that according to this equation 2, square root of 5 times CD equals to 8 minus 5 is 3. Here we divided this equation 2 by square root of 5, and finally found out that the missing side CD equals to 3 over square root of 5 units instead. This is the missing side CD, that is equals to 3 over square root of 5 units instead. Our mission is to find out they have this green shape, or in other words, our mission is to find out they have this green right triangle DCB. And so the area of any triangle equals to the base of the triangle times the height to the base over 2. We choose the base is CD, the height is CB. Repeat again, the base is CD, the height is CB divided by 2. CD is 3 over square root of 5 times CB is, again, here CD is 3 over square root of 5 times CB is 4 over square root of 5 divided by 2. So there the green shape equals to the value of this expression. The value of this expression is 4 times 3 is 12, and square root of 5 times square root of 5 is 5 divided by 2. 12 over 5 over 2 is 12 over 5 times 2, so it is 12, and 5 times 2 is 10. So there the green shape equals to 12 over 10 square units. We divided both the numerator and the denominator of this number by 2. 12 over 2 is 6, and 10 over 2 is 5. So in conclusion, we found out that the area of this green shape equals to either 6/5 square units, equals to either 6/5 square units, or in terms of numbers, the area of this green shape equals to 1.2 square units. So in both methods, we are to the same result. Okay, thank you very much.